So, welcome back for this advanced manufacturing and process modeling course. So, we were talking about the sintering module of the course. So, we have discussed about different powder processing techniques and also different powder preparation techniques as well. And so, we have started with the micro mechanisms of the sintering process, which is the heart of it. Sintering is the final step in powder metallurgy, and it is basically giving the strength needed for the powder aggregate, because it is the sintering process where we are achieving the densification, diffusion driven densification of the powder aggregate to achieve the final shape of the part. And so, we were discussing about the mass transfer mechanisms. So, in the last class we have also discussed about this equation. So, that is x by a to the power n is equal to k to the power minus m into t. So, where x is the radius of the neck, a is the particle radius, and t is the time of sintering. So, as we have discussed also in the last class, that in the mass transport mechanisms of sintering there are several components like lattice diffusion from grain boundary, from surface, from defects, and then boundary diffusion from grain boundary, surface diffusion from surface, as well as vapor phase transport. So, continuing with that, you can see the, so here this is the function of t. So, it is basically nothing but x by a to the power n is equal to f t function of t into t. So, that is so here for different mass transfer mechanisms we have listed in this table the that is the function of t, that is what it is for viscous flow, for vapor phase transport, for surface diffusion, lattice diffusion, and grain boundary diffusion, and the parameter n and m. So, that is because so there is a to the power minus m is also there in the previous equation, you can see. So, so it is basically f t a to the power minus m into t. So, then the values of n and m are listed for all individual mass transport mechanisms which are dealing with the sintering process. So, relating compact shrinkage to center approach of the particle, Kingery and Berg has given this expression, that is delta L by L 0 is equal to h by a is equal to k t to the power n, where delta L is the linear shrinkage for the original length L 0, h is the half of the distance of approach of two particle centers, t is the time for sintering, and k and n are the appropriate constants. So, German and Munir has given by evaluating the changes in the surface area of the powder system. So, change in surface area is with time, sintering time can be expressed as dAs, ddt of As is equal to minus k into delta As to the power m, which can be further expressed as ddt of As is equal to minus Bs by alpha g As 0 to the power alpha g into As to the power alpha g plus 1, where As is the surface area, delta As is the change in surface area, k is the rate constant, m is the exponent related to the reaction mechanism, and Bs is the coefficient related to the process, and alpha g. So, it is basically exponent related to the growth mechanism, and As 0 is the initial surface area. So, these are the different mass transport mechanisms that is given by for different scientists, and also you can see in this table we have you can see that the for the appropriate expression for different mass transport mechanisms involved in sintering is given. So, then so sintering deals with the pore closure and development of microstructure. So, it is basically the diffusion happening between the neighboring powder particles is responsible for finally generating the grain morphology, microstructure in the sintered compact. So, grain compact is combination of particle plus pore. So, in the beginning of sintering, grain boundaries form in the contact area between the particle. So, assume this is a 2D image of a powder particles. So, you can see that there are some pores in the grain boundary triple point, and also I mean, so because this is we are talking about green compact. So, green compact means, so these are the locations where mostly the additive or the polymers are occupying, that we are generally adding with the powder mixture, so that it becomes flowable and it is capable of attaining a particular shape. So, but there you can see that there are some contact regions between neighboring powder particles. So, these are the regions which are I mean forming the grain boundaries at the beginning, and we have also discussed about the neck formation mechanism, and also discussed about the GB tensile and GB compressive. So, like for the convex region, it is basically GB tensile, grain boundary tensile, that is formed, and in the concave region, and in the convex region, that is the compressive stress, that is GB compressive, that is what forms, like we have discussed also in the earlier classes. So that is what we have discussing again for your ease of understanding. So, here you can see the growth of neck leaves a continuous network of pores and BR relation with grain size of the particles surrounding them, which is termed as Jenner relationship. So, further sintering establishes continuity of pore network, which breaks down, of course, because initially the pores which are present which are present after removal of the polymeric ingredients or additive ingredients by the debinding mechanism, be it solvent or the thermal debinding. So, then the pores are connected to each other. So, it is a continuous pore or it is a kind of open pore. So, those are transformed into close porosity as and when the sintering progresses and the diffusion happens between the particle adjoining location surfaces. So, then the grain boundary forms there, like we have discussed over here. So, that is also responsible for making the pores isolated at the grain boundary location. So, during final stages of sintering, densification plus coarsening of pores plus grain coarsening. So, this is very important to understand. So, these are all three mechanisms that happen simultaneously. So, but of course, there is a scheduling between them. So, then densification, you can term it is the first step, and then once the a certain densification happens, then the pores which are present or which are trapped in the grain boundary triple points. So, then these pores basically they undergo coarsening with the progress of time. That means, if the generally in case of sintering we kept so if I draw a typical sintering cycle, so I assume this is the temperature and this is the time. So, then it happens like this. So, there is a isothermal period involved, where we can see it is that the process governs as a function of sintering time. So, within that time, so initially the densification is achieved till this phase, and also to up to some extent at the beginning of the holding time, and then these two mechanism becomes prevalent. Simultaneous coarsening of the grains already formed, and also coarsening of the pores that are trapped between the grain boundary triple points. So, this is what happens during the final stages of sintering. That means, it is towards this region. So, so by either it happens by either diffusion mass flow between the pores or by coalescence of the pores during grain growth. So, choice of sintering temperature and other parameters that determine the diffusion behavior is critical in controlling the grain growth and minimizing the residual porosity. So, that is what So, there are a number of variables in case of sintering. For example, the heating rate, that is the dT, that is the heating rate, that is a very important parameter, that is heating rate, and then there is the isothermal holding time, that is HT. Okay. So, and also the initial powder particle size, and also the kind of additives or kind of pore morphology that is present. So, it is the three most important variables affecting the sintering process is the temperature, that means sintering temperature ST, then the heating rate HR, and the holding time, that is HT. So, if these parameters are not chosen appropriately, for example, if there is a higher holding time given than needed, then it will cause significant grain as well as pore coarsening, and in turn it will significantly degrade the mechanical and even physical properties of the sintered powder compact. and also like if the temperature, that is sintering temperature, is not sufficient, then there won't be enough densification, and we may not be able to achieve the required sintered density that is expected from the part. So, and that will also result in higher amount of residual porosity. So, that is why optimization and idealization of these important sintering parameters variables is of necessity to achieve the desired microstructure and properties from the sintered parts. Okay. Moving ahead, so we will talk about the neck growth rate equations at different stages of the sintering process, and also during different mass transport mechanisms that takes place during sintering, that we have already discussed about it. So, this table gives a summary of the mechanisms like stage 0 adhesion. In that case, neck growth rate equation can be expressed like this, that is x dot 0 is equal to C A by A square by x. So, here we are all talking about the neck growth rate, that means dx by dt, which is identified by, so for stage 0 the I mean the subscript 0 denotes that it is the initial stage or stage 0. Stage 1, so subscript 1 is denoting the stage 1, that is the stage 1 neck growth, and it is the the expression, resulting expression to calculate the neck growth rate is shown over here, and then all others involved in for stage 1. So, like the vapor phase transport, lattice diffusion from surface, boundary diffusion from grain boundary, lattice diffusion from grain boundary. So, like the mechanisms we have already discussed earlier. So, other stage 1 mass transport mechanisms. So, the corresponding neck growth rate equations are shown over here. So, from here, so and also in case of stage 2 and stage 3 of the sintering process. So, the diffusion mass transport mechanisms are boundary diffusion from grain boundary as well as lattice diffusion from grain boundary. So, these are basically the neck growth rate analogous neck growth rate equations. So, from these individual equations you can quantify the role of individual mass transport mechanisms in case of sintering at different consecutive individual stages of sintering, that how much which mass transport mechanism contributes to the neck growth process and the densification process. Okay. So, then we will move to the liquid phase sintering. So, liquid phase sintering is also a special kind of sintering. So, we basically do liquid phase sintering to derive the benefit of bringing down the sintering temperature, and also to enhance the sintered density by promoting the sintering kinetics and also the densification mechanism. So, the variations are normal liquid phase sintering. So, liquid forms from one or more components in the original green compact, and infiltration. So, so in this case normal liquid phase sintering, it is the liquid that is getting generated from the additives itself. That means, the additives that we are adding during compacting the powder aggregate. So, this additive itself gets transformed into liquid during the sintering process, and then we get the liquid phase. And the second technique is the infiltration. So, in this case the green compact is infiltrated with liquid formed outside the compact early in the sintering process. When already there are some pores gets created because of the sublimation of the polymeric binder ingredients. So, that those pores gets infiltrated by the liquid generated outside, prepared outside. So, this can happen, this can also happen after pre-sintering. So, like when a pre-sintering is done with the objective to achieve some amount of density increase compared to the green density, and also when the porous network is fully evolved because the binder ingredients are totally left the powder compact. So, then there is enough porous architecture forms within the body undergoing sintering, where the liquid can be infiltrated, and then it can be proceeded with the liquid phase sintering further. So, the stages, what are the stages of liquid phase sintering is, number 1 is the rearrangement, that is the liquid flow. So, particles rearrange due to liquid phase, that is what is shown over here. So, that means the rearrangement phase, it is the convection of the liquid generated at the interparticle spacings, that bringing the particles closer to each other and they establish connection between the particles. And then number 2, second stage is the accommodation, that is dissolution and reprecipitation. So, in this stage it is basically the Oswald repelling mechanism that we have discussed earlier also, where we can see the evolution of the growth of the bigger particles at the expense or dissolution of the smaller ones. So, like this is the example of the Oswald ripening that happens in the second stage, that is accommodation stage, and then the final solid state sintering stage, where we have also discussed earlier. So, for your understanding I am discussing again, where the contact from the contact points, that is establish the contact points from there, because the even in case of liquid phase sintering, the final stage is solid state sintering only. So, where coalescence prevails, coalescence, because of coalescence only we see the neck growth and also formation of grains in the powder aggregate undergoing sintering. So, these are the stages. So, the densification kinetics, what is that? So, the liquid content up to 35% improves initial densification, and coarse particles or high green density reduces the melt's favorable effects. So, that means there is not enough path for the liquid which is formed if the porous network is getting constricted due to the presence of coarse particles or higher green density, that means higher powder loading within the compact. So, in that case there is not enough path for the liquid infiltrated or generated in situ within the powder compact. So, that is why the effect is also decreases, and favorable effects of liquid phase sintering are not pronounced in that case. And then number 3 is ineffective second stage may lead to swelling due to particle separation. So, so that is why so that is why if the particles, because I told you that in the rearrangement stage the goal of this liquid also is to by convection to draw the particles closer to each other, say particle A, particle B. If they because the densification or the diffusion mass transport processes starts from the contact point. So, if they are not in touch, then they cannot be joined together or they cannot coalesce together to generate the fully formed grains. So, hence the liquid phase sintering become effective if the particles get swelled away from each other because of the improper presence or improper flow of the liquid matrix that is generated in case of liquid phase sintering. So, the applications are, it is widely used in sintered steels, cemented carbides, heavy alloys, bronzes and silicon nitride systems. And also like in our group also we are working with aluminum nitride, where liquid phase sintering can be benefits can be significant, where we can basically bring down the sintering temperature of aluminum nitride to around 1750 to 1800 degree centigrade, although the sintering temperature for aluminum nitride in case of solid state sintering varies between 2000 to 2100 or even beyond, based on the particle size. So, this is a particular benefit in terms of lowering the sintering temperature, and this is basically the different stages of the sintering that is shown by showing the variation between sintering time and the densification parameter. So, it is the initial stage, that is liquid flow, which is causing the rearrangement that I have already drawn in the previous slide and expressed to you, and then this is the solution reprecipitation, which is connected with this Oswald ripening process, that also I have expressed explained to you earlier. And then finally the solid state sintering, when the coalescence takes place between the neighboring powder particles which are in connection with each other. And so, the activated sintering is also it is called as activated sintering, liquid phase sintering. So, sintering where activation energy is lowered by adding chemical activators or dopants, which are responsible for generation of this liquid phase, which is enhancing or making the fast tracking the diffusion kinetics. So, hence we can get the higher higher density in the sintered parts. So, the benefits, densification kinetics can increase up to 100 times for certain refractory metals. Common activators palladium and nickel are most effective. as an activator or for generation of liquid phase mechanism, that nickel salts are reduced to metallic layers on tungsten powder, forming a thin monatomic layer to enhance sintering efficiency. Okay. So, I mean, so we will progress further details about the liquid phase sintering. So, it is used for multi component system with at least one of them having lower melting point, or it is for tungsten, tungsten carbide, ceramics and rare earth, which are having otherwise very high sintering temperature, and also the diffusion kinetics is not is very difficult to achieve the desired I mean density, that is close to theoretical density in solid state sintering alone, and also where accelerated sintering is on demand. So, the stages are like I already told, first stage, that is rearrangement. So, initially the liquid phase wets the particle, leads to rearrangement of the particle and densification. Capillary pore size decreases with sintering. So, stress from the surface tension of the liquid phase increases. Shrinkage from the viscous flow, which can be expressed as delta L by L 0, that is linear shrinkage of course. L 0 is the initial I mean dimension, a linear dimension, delta L, the L is the change in the linear dimension, is equal to k, which is the constant, is into t to the power 1 by 1 plus x. So, x is a small fraction. So, in the second stage, which is called the solution reprecipitation stage. So, the solid phase dissolves in the liquid and reprecipitate elsewhere due to the differences in solubility of small and large particles. So, in this case, so it can be expressed, I mean the Oswald ripening that I have told you earlier also can be expressed by this Gibbs-Thomson equation, which is of this form. So, S minus S 0 is equal to 2 gamma S 0 omega by R t into 1 by r. So, S and S 0 is are the solubility of the particle with radius r and that of a flat surface. So, omega is the atomic volume. So, solution reprecipitation can be rate controlled by either one of the two steps, that is dissolution and diffusion. So, I mean so delta L by L 0 cube is equal to k 1 t by r to the power 4, where k 1 is the constant related to the diffusivity of solid in the liquid. So, for interface reaction control, the shrinkage follows for this expression, that is the I mean change in linear dimension delta L by L 0, that is the initial dimension squared, is equal to k 2 t by r square. So, here k 2 is the constant related to reaction rate of solid in liquid. A skeleton of solid phase with liquid squeezes out to larger voids in the solid and onto the surface is shown over here. So, in the third stage you can see the solid skeleton sinters like solid state sintering and liquid phase. So, I mean so the mechanism is shown schematically over here. So, this is the base additive. So, you can see that these are the binder ingredients that they are added at the very beginning when we are making the powder compact, I mean when we are preparing the powder compact. So, this is for the first route. They are also like possibility of adding the liquid phase by melt infiltration, that can be done, I mean after in the pre-sintered state where already a porous network exists in the pre-sintered powder compact. So, but let us take the example of the first case, that is where we are adding the additives which are basically transforming into liquid when at the beginning of the sintering. So, so this is the schematic which shows that. So, then so after this first stage we are basically getting the second stage. So, that is I mean which is termed as the stage 1, or I mean the liquid spreading, or I mean on also the rearrangement stage that we have discussed earlier. So, this is stage 1, then this is stage 2. So, that is basically the stage when the solution reprecipitation is happening, which is dominated by Oswald ripening. So, from here it is coming to here, and then from here it is going to there, where there is it is the third stage when the interparticle contact is getting established, and it is basically the solid skeleton is formed, and it is primarily I mean governed by the principles of solid state sintering. So, here the second coarsening mechanism, I mean or the mass transport mechanism, that is coalescence, that becomes prevalent in this case. So, in this case you can see that so this is the point of contact is established. From there it is basically the neck forms between the particles and they grows, and then they become fully diffused to each other, and then we see the formation of grains in the sintered compact. So, I mean, so here this is the example is shown in case of I mean tungsten nickel iron alloy powder. Okay. So, then loose sintering. So, it is widely used as a for producing highly porous parts such as filters. Metal powder is poured or vibrated into a mold and heated to the sintering temperature in a controlled atmosphere. So, we have already discussed about the loose sintering. So, this is just a kind of a recap. So, for your understanding or your I mean so that you can differentiate between the liquid phase sintering and loose sintering, I mean the contrast between both of them. So, like in liquid phase sintering, loose sintering, we are basically just vibrating the mold to arrange the powder particles in the desired shape of the compact that is expected to be obtained, and then they are heated to the sintering temperature in a controlled environment. So, the process depends on the powder's flow characteristics and allows shapes that can shrink during sintering without cracking. So, the mold requirements are easily machinable or formable into the desired shape and able to withstand sintering temperatures without deformation, and it must be resistant to welding with the powder during sintering. So, these are basically primarily the requirements of the mold, and then so in case of, so I mean this is the I mean graphical representation between the volume of liquid and density percentage in case of liquid phase I mean sintering. So, you can see that it is the so with the increasing of volume of liquid, if you I mean so these are the stages. So, if the volume of liquid increases, then basically there is rearrangement, and then we cannot basically achieve the benefit of all the 3 stages get activated. So, up to the a certain volume of liquid, if we follow the keep concentrated to that, and if you take ahead, then we can even achieve density up to 100%. So, then in that case we can achieve the all 3 stages, that is rearrangement, that is the stage 1, and then this is the solution reprecipitation where the Oswald ripening is effective, that is stage 2, and then the final stage, that is solid state sintering, that is stage 3. So, we can even theoretically we can even achieve 100% of the theoretical density of the powder material. Of course, it is not the case in reality. However, we can reach pretty close to the I mean theoretical density of the material in case of liquid phase sintering. Okay. So, I mean so there so it follows by the, now we will discuss about the theory of sintering. So, where we will establish the effect of different process variables involved in the sintering process and how they basically control the sintering mechanisms and also the properties of the final sintered parts. So, I mean so the most important factors involved during sintering process are temperature, sintering temperature, sintering time, and also the I mean the holding time and the furnace environment. So, the influence of these factors on the sintering process is, well, for example, number 1 is sintering temperature. So, increasing the sintering temperature greatly increases the rate and magnitude of any changes occurring during sintering. So, I mean so the effect of sintering temperature for a constant green density you can understand from this figure. So, you can see for a same temperature, I mean we can get like if we just get higher green density with the increasing I mean temperature. So, it is for same temperature, if we just increase the time, then we also can get higher green density. So, I mean so basically it is sorry, I mean you can understand it in the other way around. So, if we are starting with the same green density, I mean then also we can see that at the same temperature we can get, I mean at a higher temperature we can get higher sintered density with the increasing temperature. So, you can see it is the sintering time is a constant, and then I mean although I mean for a same green density like this curve and this curve A and this curve B, for material A, material B having same green density, but the sintered density at if we talk about at this much sintering time, we can achieve the here I mean the value say D prime, and here the value say D. So, D is much higher than the D prime. So, this is because of the increasing sintering temperature. Okay. And also so, in case of I mean increasing green density for the same temperature, like I mean for the same time, if we in this case again, so in this case when we are keeping the sintering time as constant and the sintering temperature, so time is equal to constant, sintering temperature is equal to constant. So then I mean we are just I mean talking about a initial green density. So dgr of material A, dgr A and dgr B. So then if dgr I mean B is higher than the green density of the material A, dgr A, then of course for a constant sintering temperature and constant sintering time we can get this equation is also prevalent in the sintered density. So ds I mean B will be higher than the ds A, even then when we are dealing with a I mean constant sintering time and constant sintering temperature. So, with this we are done with this class, and we will meet you in the next class, and we will discuss further about the I mean mechanisms of sintering and how different process variables affects the sintering kinetics. So, thank you.